Dr. Barry W. Boehm is the University of Southern California Distinguished Professor of Computer Science, Industrial and Systems Engineering, and Astronautics, the TRW Professor of Software Engineering, and Founding Director of the USC Center for Systems and Software Engineering. He is also the Chief Scientist of the DoD Stevens USC Systems Engineering Research Center and a part-time employee of the Aerospace Corp. He was just recently selected as Top Professor of the Year for 2019 by the International Association of Top Professionals.
Over the last 25 years, I've had the privilege of interviewing and highlighting some truly interesting people. Everyone who is anyone, both the famous and the infamous. From presidents and their first ladies to kings and queens, movie stars and pop stars, captains of industry, heads of state, sports personalities, innovative entrepreneurs, and some pretty fascinating everyday people. Today, I'm proud to introduce you to Dr. Barry Boehm, a distinguished professor of engineering and researcher who can proudly say he has educated over 2,000 master degree students in software engineering and over 40 PhD students. Sir, I can say for certain you are a teacher's teacher. So let's start by going over your educational background. Dr. Boehm, how did you build the foundation to start your career?
Ricardo Valerdi here from the University of Arizona Department of Systems and Industrial Engineering, and I'm joined by Professor Barry Boehm from the University of Southern California Center for Systems and Software Engineering. Thanks for joining us, Barry.
You're welcome.
So let's talk a little bit about software cost estimation, which is your contribution to the profession. And in particular, I'm wondering if you could say a few words about how you got started in this area.
$1 billion IT procurement for the federal government in this new, very complex environment. So when I ran into them, again in 2009, they were doing a lot of research on real option theory and deferred commitment. And what came out of that is something called the incremental commitment model. And here to tell us all about it and to tell us a little bit about some of the research that they've been doing in Kanban, please welcome Barry Boehm.
Hello everyone, I'm Mr. Knowledge. Do you guys know who invented the COCOMO models? If not, let's get to know him better.
I'm Brad Clark and I've known Barry Boehm for 28 years.
Good afternoon. Hi Barry, and hello meeting attendees. In case you don't know me, my name is Maria Pinedo.
Hello everyone. Here are some of my recollections about Barry Boehm's influence in my life.
Hi Barry. Hi everyone.
I'm Doug Rosenberg from Carroll Agile. Dan Liggett here.
Hey Barry, this is Scott.
For the work that I've done.
I'm David Seaver.
Hi, I'm Frank Bells.
Your technical contributions to both cost.
Hi, this is Dave Zubro.
Hi, I'm Judy Turner.
Hello, my name is Neil Siegel.
Hey Barry, it's Dan Strickland from Huntsville, Alabama. Software.
Next, Dr. Boehm's interest. His research interests include
You are watching a man designing and analyzing an air-launched satellite vehicle with the aid of a computer. Using computers to design aerospace vehicles isn't new. What may be new to you is the way the man is using the computer and communicating with it. Here he is directly specifying his design and flight plan with the light pen and online keyboard, then watching graphs of the resulting vehicle performance on a TV-like display screen as the vehicle's trajectory is being computed. Traditionally, computer assistance has been a much longer and more tedious process for the aerospace engineer. involving the manual transcription of design curves and parameters onto key punch forms, the 2-hour to 2-day delays for key punching and for each computer run, and the manual transcription of numerical computer printouts into performance curves. Most maddening of all are the inevitable trivial errors which are recognized and corrected within seconds of seeing the output, but still consign the engineer to another 2-hour to 2-day wait for his corrected results.
I was born here in Santa Monica. I went to grade school, junior high school in the Santa Monica schools. And then I went to Harvard University in Cambridge, Massachusetts for my undergraduate. I was a math major all the way along. I was fairly good at math. Well, I guess I wondered what a math major was going to do for a living, and it seemed like you could be an accountant. A lot of things seemed sort of boring. Fortunately, after my second year at Harvard, I came back to California and got a summer job, and I went to the personnel office, and they asked me what my major was, and I said mathematics, and the guy looked at his blackboard and said, well, there's thermodynamics and propulsion. There's something called digital computing. We have a digital computer, and that seems like it's math, so why don't you go there? So fortunately, this was General Dynamics, which was developing the Atlas rocket, which was going to be one of the rockets that send astronauts into space. And all along I was a fan of science fiction, and so here I was being able to build computer programs that are going to help astronauts go into outer space and things like that. So it sort of directed me in that direction. So when I graduated from Harvard, I came back to General Dynamics and continued to do computer programming that was helping analyze various things. That one of the things the Atlas rocket needed was an escape hatch, and if something went wrong with the rocket, you could push a button and a little minor rocket would push the astronaut away from the big rocket that may be in trouble. And so I got to develop the computer program that enabled that to work. And so again, it was an opportunity to contribute to going into outer space and the like. And again, each one of the big aerospace companies had a German rocket scientist, and Kraft Ericke was the one at General Dynamics, and I was able to do some things for him.
David, I'd like to throw in a story about Barry that he probably doesn't recall, but I think fits in very nicely. So you talked about making the transition from a hardware-oriented world to a software-oriented world, where software is the big thing and there's a crisis and so on. So this would have been around 1971 when I was a brand new PhD, and I had just started my academic career at the University of Colorado. And I was sitting in my office. I had just gotten done with my PhD in combinatorics and had a strong interest in programming and in software and so on and so forth. Not sure what to do with my life and my career in a brand new computer science department that had, I think, 4 faculty members at the time. And in the fall of 1971 was delivered to my office a copy of Datamation magazine, which at the time was a serious publication venue. And in Datamation magazine was an article written by one Barry W. Boehm, and it was called CCIP 85, which was a study that he had done at Rand Corporation with some colleagues about what the shape of the computing world would be like in 1985, which was then 14 years in the future. And lo and behold, Barry had projected that by 1985, the current ratios of cost of hardware to cost of software would be completely turned upside down. So in 1971, hardware was 90% of the cost and software was a 10% afterthought. And Barry projected that in 1985, software would be 90% of the cost and hardware would be incidental 10%. And that was so heartening to some of us that we decided that this interest we had in software was probably a good thing to stick with. And it was absolutely formative for me. And I've often reminded Barry this, and in 1984 I asked him, would he be publishing a CCIP 99? And that's what he did. He laughed just exactly like that.
History interviews with Jay Last, who was one of the people responsible for the silicon integrated circuit, and which, was of course part and parcel of this missile work, ICBM work, and in those interviews he made a point to say you also have to understand that it was a scary time on the world scene. So that's not to be forgotten as a context.
Yeah, and I got involved in the ARPANET basically because of some of those kind of things. That the Minuteman missiles had various kinds of communications support things that were basically wires, and so there were concerns that if either airplanes or missiles came along and cut the wires between these things, that they couldn't receive their messages to fire or things like that. And so the packet switch network approach looked like it might be a good solution for that, and I got involved in analyzing those kind of things. Coincidentally, it was my wife who was the key contributor to this, and Paul Barron was the engineer who was doing this series of 14 reports that said, yeah, here's how you can do packet switch networking, and here's how you can reassemble the messages at the other end, and here's how you can transmit things, and here's how you can worry about overloads and the like. And so she was programming during this year, and Paul Barron said, yeah, I need somebody to simulate these and make sure that this kind of routing is going to succeed. And so she produced something, and basically showed that it could address all of the potential problems using the kind of algorithms or some variations of some algorithms that. And Paul was a nice guy, and he named her the first author of that report. And so She really has a minor place in the history of the ARPANET and Internet and the like. So I worked for RAND Corporation for about 14 years. When I first got there, they put me in a basement called pre-clearance. You needed to have a security clearance to go into the main building. And so there were a few of us that were down in the basement, and they would give us some computer programs to write, and we'd write them up and give them back. And it turned out there was another math major in pre-clearance, and she also went through Santa Monica schools and was a school teacher as well, and we hit it off, and we ended up getting married. So yeah, at TRW, I was involved in 2 generations of building a corporate software development environment. So the first one was about the first time that we had local area networks, and so we were getting people in networks together, and we actually used the COCOMO model to estimate whether we would be able to improve productivity. That the company is a conglomerate whose biggest thing outside of defense is auto parts, and they were sort of psyched by the Japanese 5th generation initiative, and said, everybody in TW has got to get more productivity. And if you have a good proposal for it, we have corporate funds to do things with it. So basically, we came up with a plan for this, and I used the COCOMO model to say, if your tools are better than this, if you've educated your people in these technologies, you ought to be able to double productivity in 10 years. And we put that forward, and my division general manager thought this was a really good idea, but he said, we've got to hook you up with an upcoming project so that we know that what you're doing is going to fit what they need. And that turned out to be really good, because in a lot of cases, I hired a couple of people, Art Peister, who had been at UC Santa Barbara, and Lolo Pinedo, who had just graduated with a PhD from UCLA. And so we had a very strong technical group of people, and they had a lot of good ideas for automated test case generation and things like that. And the project people said, what we'd really like is anytime we make a change in a document to put a little bar at the right that says this thing has been changed. This re-baselined everybody as far as what the real project's priorities were going to be, and things like that. So at any rate, we built one, and it really did double productivity for that project, and did for a bunch of the future ones. And in looking at things, we found that most of the time people were producing documents and filling out forms rather than writing computer programs. And so we made sure that the secretaries would get on this. And so this improved productivity a whole lot, because the software people didn't have to retype things and the like. And we looked around for technology and forms management, and found that the IBM and DEC and the like had some things that they were pretty clunky, and we felt we could build a better forms management system than they had. So we did, and we ended up with the world's best 1982 forms management system. By 1986, we still had the best 1982 forms management system, and because we were amortizing its maintenance over one company, and the computer companies were amortizing it over lots of things, so they got a lot better. So we did a second generation where we were doing much more commercial technology involved in it. So around that time, DARPA was getting interested in software engineering environments, and there was this project called Arcadia that Lee was involved in, and Dick Taylor and a number of people from UC Irvine were involved in, and we became sort of their industrial counterpart, and saying, here are some things that would be valuable to make sure that the industry people would be interested in them, and making some contributions, like Lola Pinedo came up with the Project Master database and that sort of thing. So DARPA got quite interested in Arcadia, and there were various other things that I was doing that connected me with DARPA. And at that time, the director of the DARPA Information Science and Technology Office was a really outstanding mathematician named Jacob Schwartz. Unfortunately, he was somebody who wanted to put his hands on everything that was going on in the office and sort of micromanage the program managers. And he basically had a disinclination to do things that weren't mathematically oriented. So he wanted to kill the artificial intelligence program. And so when I got there, there was a proposal and a draft budget to do that, but I got some of the AI people to come and say, should DARPA really do this? And what kind of things, if we keep it going, do you think are going to make a difference? And so we got the Marvin Minskys and the Ed Feigenbaums and the like together, and they made a pretty strong case, and so I was able to sell the DARPA director in putting the money back into AI, which was probably, in the first month I was there, the most important thing I ever did. Since it just sort of took off like a rocket a few years later. And when I was 55 at TRW, I said, well, I could spend another 10 years here and retire at 65, or I could go and try and do something else. One of the fortunate things I had was an opportunity to do some things for the number 2 person in the TRW company, Simon Ramo, and the R in TRW was for Simon Ramo. And one of the things that he wanted me to do was to come up with a program that made some of our software people more diversified. He said that the best engineers at TRW are T-shaped people. Basically, they're very deep in one discipline, but they're pretty good in a breadth of other disciplines. And most of our software people were I-shaped. And so I said, yeah, what I would like to do is go and become a professor at one of the UCLA or USC and create a program that would educate T-shaped computer and software people. Doing something else. And one of the things I was most frustrated about at TRW was hiring computer science grads who knew a lot about compilers, but hardly anything about software engineering. And so coming to a university and trying to teach them how to do real software engineering was really the stimulus for doing this. And so the two things that we got started, one was the master's degree in computer science with specialization in software engineering, and the other was the Center for Software Engineering initially. It eventually became the Center for System and Software Engineering. Fortunately, we were able to attract a number of industry affiliates and get some support for doing a bunch of research, and eventually that got followed up with government contracts and things like that. And so we've been going at it ever since. Okay, so one of them has been evolving the course from something that was sort of doing makeup projects to something that does 15 to 20 projects for real people in the USC community every year. About a quarter of these are on campus, about a quarter of them are local government, about a quarter of them are local social services, and about a quarter are local small businesses. And so it's a good way of connecting with the community and The students really enjoy doing things where they're actually building something useful for people and learning how to do it as they go. So the other kind of research projects that we've been doing are tools that help us make these projects go well, like risk management tools and progress tracking tools and requirements negotiation tools. Other ones are things that the affiliates wanted, like cost models that estimated software cost the way it's being done in the 21st century rather than the 20th century, and branching out into models that would estimate quality, estimate system engineering costs, estimate product lines, and things like that. And in between, we found that there were a number of needs for tools that would help you analyze architectures or incompatibilities with COTS products, or do better jobs of testing by testing the high value things first and inspecting the high value things first. And so that's the kind of thing we've been doing. Okay, the future is just sort of a run on the treadmill and try to anticipate where the field is going. So right now the field is going toward social networking and big data and nanotechnology with millions of sensors gathering more and more data that you have to analyze, and a number of other trends towards systems of systems and more complex systems where everything has to talk to everything else and understand everything else. And so these are challenges that we have in building useful things for the clients, but also our affiliates have in building useful things for themselves or the government or users or social services or whatever. I would say the biggest legacy is now close to 50 PhD graduates. So some of them are running companies now, some of them are doing really frontier research and the like, and some of them are becoming professors and turning out the next generation of PhD graduates and the like. So I'd say that's sort of the biggest thing.